So please welcome to stage Florian.
Thank you very much, and welcome to the 4 Pillars of Observability with me. My name is Florian. I'm working at the profiler team at Datadog, where I'm building a continuous profiler for the PHP language. Besides that, I'm an open source contributor. I contributed namely to stuff like GraphQLite and PHP Unit. I also contribute to the PHP core itself, to the PHP documentation and the internals book. And not so recently, I became the maintainer of the Parallel extension, which allows you to do multi-threading in PHP. So if you ever have a CPU-heavy problem that you can break down into smaller problems, check out Parallel. You'll love it. And I'm doing all of that, although I'm married with 5 kids, of which 2 of them are currently roaming London, and they'll join us at the after party. So back to the story. We had a customer that had customers. Those customers were complaining that used to be faster. So they reached out to us, wanted some help with how to find out what's going on, what the problem is. So what they had is they had a CSV upload API endpoint where customers could upload merchants could upload their catalogs to their backend system. And they complained that the P95 latency, like basically they monitored the API of the customer of where they're uploading the stuff, and they complained that the latency was going up over time. This is the kind of problem that's a bit hard to debug because there was no obvious case and no single event, we did this deploy and then it suddenly changed, but just gradual degradation over time. But what we have is we have a lot of observability tools. We have metrics, logs, traces, profiles, the 4 pillars of observability at our hands. So we wanted to use them to solve the problem. I'm going to show you what they are and how they help us to solve this problem in particular. So the first one is metrics. But what is a metric? Well, the Wikipedia defines this as a numerical value representing something at a specific point in time. Which is super theoretical. I'm a practitioner, so this tells me nothing. But what tells me something is that think of it as a car dashboard. In a car dashboard, you're going to see the current speed that you're going, you see your battery level or the engine temperature, stuff like this. In our world, that would be stuff like the CPU, memory, requests, latencies, errors, stuff like this. And if you add a timestamp to that, then suddenly what you have is a metric. You have a measurement at a specific point in time. There are 2 types of metrics. There are work metrics, which is basically work metrics measure the useful output of your system. So basically you can say everything that your actual user experiences. Stuff like the request per second, response rates, which error codes you're sending, your P95, P99 latency, all of this are work metrics because this is what your customer actually sees and feels. Then on the other hand, there are resource metrics, which is just the measure the health of your infrastructure. And infrastructure is not only your hardware, like your CPU and memory usage and how much disk space you're going to have left on your devices, but this is also services that you're using, like the saturation of queues in Kafka or in RabbitMQ if you're using that, or your PHP FPM pool size, or other stuff like availability and uptime. Because metrics are super easy and cheap to store, the best practice is just collect as much as you can, because it's cheap to store, but it's very expensive if you don't have the data afterwards if you want to look in this. So usually metrics are stored for up to 2 years. So that makes it also super nice because you can see what happened this week, the same week last year. You can overlay the data and then you can see how you grow over time. But metrics alone can already solve problems. And I want to quickly sidebar a story for you here. That was roughly 15 years ago. I was working in a different company. It was an e-commerce retailer. And we were all in office and we had a big television on the side of the office. And that TV was connected to a Raspberry Pi, and that was just showing the dashboards of some of our observability tools. So we would always see stuff that is going on in our production environment. And it was 5 minutes to lunch break. We were already talking about where we want to go. And when we were about to leave the office, we saw this on the dashboard. So there went our lunch break. So we went back to the computer, back to our desk, and checked what was going on. This is the time to first byte in seconds. You can see it was below 1 second, and then it started rising up to this peak of 6-7 seconds, and then suddenly it was peaking up to these 11.3 seconds. This is not what you want to see when you're about to leave the office. So we went back to our desks, checked the other dashboards, what we see, what was going on. We thought that there was maybe a lot of incoming new traffic. So we checked and we saw that the PHP FPM workers hit PM max children. So PHP FPM was not able to spawn new children. We also saw that the database connection was rising, and we immediately saw, well, there's an uptick in incoming traffic, maybe a DOS attack, maybe just the marketing department decided to have a new campaign that is way more successful than they anticipated. But that was not the case, because we were seeing that the CPU was going down and approaching idle on the FPM, on the PHP machines, and also on the database machines, which is very weird. And the system was completely unreachable. We were not able to go onto the front page anymore. So all of this showed us already that the culprit is the database. Something is not working anymore, but blocking. And it's basically just the database not responding to SQL queries anymore. Probably it's just deadlocked, or those queries just take a lot of time. So what happened is we checked the database and we saw a ton of replace into statements on a caching table and the same ton of delete statements on the same caching table. And we replaced that with an insert on duplicate key update. And the thing we learned that day is that replace into is not actually doing what we thought it would do. We thought it would do exactly what the insert on delete key duplicate key update does. But that's not the case. What replace into does, it deletes the row if it finds it, and then creates a new one. And that means that it does a delete statement in an InnoDB table, and if the row that it wants to delete does not exist, then InnoDB does do a gap lock. That means it locks the entire gap between the two index values that are there, where this index would have been if it would exist. And this gap can be enormous. It could technically be your entire database. And then other delete statements on the same table would also just lock and wait for all of these statements. And that's how we experienced that InnoDB has a gap lock. Basically, we can just switch it to this insert on duplicate key update, which will do exactly this. It will try to insert, and if it finds the key already, it'll update. So actually, in the end, lunch was late, but we learned something. That was a good thing. And we only need metrics for this, no other tool. So back to our CSV mystery. We checked the metrics to see what was going on, and metrics told us that everything is fine. We had the P95 latency slowly creeping up. We could see this, but we could also see that CPU usage was normal, memory usage was normal, database, PHP, FPM pools, all of these, everything was just normal. There was nothing really shining out. So nothing was really unusual. So we need more context and see what's actually going on. For more context, we looked into the logs because there were log files. But what is a log? A log is a time-ordered record of discrete event that describe what a system did and why it did it. Honestly, the why part stands and falls with the content of your log message. You can write anything there, so that's up to you. There are two different types of logs that exist. There are infrastructure logs and application logs. Infrastructure logs is everything from all the services that you are using. Like you have a PHP FPM running, you have MySQL running, you have an Nginx running. All those tools, they write logs somewhere about incoming HTTP requests, outgoing status codes, if they have to spawn a new worker or if they could shut down workers, all of these kind of things. But these are service logs. And as service logs, they know nothing about your application. So you want application logs. But what to log and what actually makes a good log? So a good log is a structured log because that makes it readable not only to you as a human, but also to a machine. There are some debug levels that you would use. There is levels there are like debug to emergency. There is also info and others. Just look it up in the PSR3. One thing that makes a good log is it doesn't kill your performance. I've seen this. Like I've seen cases where people log serialized objects. But honestly, no one's reading those 80 kilobyte log files anymore. And the other thing is, I've also seen cases where just writing logs because people serialize and just dump objects into a log file somewhere actually saturates the I/O bus of your hard drive, and your web page becomes slow, not because your CPU bottlenecked, but because your I/O bottlenecked of writing log files to a disk. Another thing I've seen, which I really don't like, is numeric error codes, because no one knows that in the middle of the night what an error code 0815 actually means. You have no idea what that is. And the general theme of all of this is we're not writing log messages for the sake of it, but we're writing log messages because in the middle of the night when I get up and I get alerted, I want to see what's going on in the system. If you're logging in PHP, Monolog is I would say, de facto standard in PHP. It implements PSL3 and it brings a lot of stuff to the table, like handlers, formatters, and processors to enrich the log messages that you're going to write. And usually you don't have to do all of this dance, because in Symfony and Laravel, I think, maybe in other frameworks, Monolog comes pre-shipped, pre-bundled with the framework. So usually the only thing you have to do is you have to tag or annotate that you want a logger in your controller, and you get a logger instance that is already pre-configured based on the configuration of the framework. And then you can just call the, let's say, info function, for example, to log a message with the info severity, and give it a name and some structured data in an array. So in this case, what we found, to boil it a bit down, is we have CSV import finished log messages, and we're going to log the user ID in the file size that we imported. So if you do this, you get a JSON that looks just like this. Basically, this is just the information that we get from Monolog. We have the message, we have the context with user ID file size. The level info matches to 200. The channel is the CSV importer channel that we created when we started the logger, and we get the date and time for this log message. The good thing about if you have this data like this is you can start correlating and searching over these things. If you would write a log message like CSV import for user ID 67890 finished with file size something, you can search for the user ID, but it's then just a full text search, and you don't know exactly what you're searching for. It would match other stuff. But if you have it like this, you can search with the right tool. You can search like, show me all log messages where user ID is this number, and then you would get everything from that user, or everything that that user did in your system. So back to the CSV mystery, check the logs. And what did we found in the logs was basically a lot of level 200 info messages, CSV import finished. If you open one of those log messages, you're going to see all the context data, like the file size, the user ID, you get the date timestamp, the level, and some extra attributes that we added. But nothing of this is actually showing that there is a problem. I mean, that's a good thing. We import still the data, but we don't know why it's taking longer. There is no indication in here. So no errors, no warnings, nothing really unusual. So we wanted to see where we actually spent some time. And that brings us to the third pillar, which is tracing. But what is a trace? A trace is the full execution path of a single request across your system. That means once it touches your entry point, let's say your Nginx or your load balancer or wherever, from there on, it's gonna ship a request. Nginx sends a request to PHP-FPM sends a request to databases or to Redis, or you might send a request to a downstream HTTP service. And a trace reveals this entire path through your system. And a trace is composed of spans. You have this one root span, which is just the HTTP request that entered your system. And from there, every unit of work that you have, let's say a logical unit of work, like a function call or an HTTP request or database query, is represented as a single span that took time. That's basically all. And a trace reveals to you which services caused a delay down the line, like things that you cannot see with metrics and logs alone. Technically, you could write a log message about when this function started and when this function exited, but you will have a hard time finding the truth in there. So a trace reveals to you the full picture of your request. In most of the cases, you don't actually need to do manual instrumentation or manually write code for tracing, but the modern tracing libraries come with auto instrumentation. That means that you just install the extension, you enable tracing, And from there on, it'll magically start instrumenting your frameworks. Like if you're using Symfony, Laravel, one of the bigger frameworks, then all of the modern tracing libraries have auto instrumentation for this. So it will show you queries to database, downstream HTTP request, HTTP request handling, or container loading, and all of these things. And you don't need to do any code changes for this. It will just work. Sometimes you have a, let's say, unit of work that you deem is very interesting for you, but it's not necessarily in the framework and auto-instrumented, but it's just something that you want. Then you can do manual instrumentation using OpenTelemetry, for example. This is just setting up the OpenTelemetry tracer, the OTel tracer, and then you have a span builder, which you give it a name, and then you start the span, because from there on you say, this is like the interesting work that is happening. And the interesting work happening is actually just the parse CSV and the import rows. And then you're going to catch an exception that might be thrown there. You can attach the exception to your span and then just rethrow the exception, and then finally just end the span. And then magically all of this work will be shown up in a tracer, and you'll see this as a span, as a unit of work, what's going on, how long it took, if it did any downstream calls to a database, third-party service, or if it threw an exception that traveled this boundary, and the span will be ended here. If you have an extension already installed, like there is an OTel extension, for example, you can also do it a bit simpler, because the problem with the earlier code path we've seen is that this clutters your business logic. You suddenly have all the OpenTel instrumentation stuff in your business logic. But if you just put that into its own function, you can just annotate with a with span and give it a name, what the name of the span should be. And then magically, the extension will start a span on entry of the function. It'll end the span on exit of the function. And if there are any exceptions that travel over the boundary of the function, it'll attach that to the span. And then you see the same thing, but you have clean business logic and just some annotations in there. So back to our CSV mystery. What does the tracer show for the HTTP request? So we see we have a unique trace ID. It's just this string here. We see we have a root span ID, which is the HTTP put request on API v2 catalog that takes 16 point something seconds. We have our custom CSV span, because we were interested in that. It's taking 15 seconds roughly. And then we have two spans, one at the beginning talking to MySQL and one at the end talking to MySQL. Roughly 5% of the time is spent in MySQL. Which is probably something one should look into, because there's a lot. But otherwise, we know that we're not, like the big thing here is what we are seeing, the big values here is stuff that we are not seeing. And we're not seeing n+1 queries. We're not seeing that we're doing a downstream request to another service that is slow. The database stuff is not too fast, but it's also not really slow. We are spending roughly 14 seconds here in this part, in this span where we're doing stuff in PHP, and we're not calling something else, so it's us. So the tracer shows us that this is the PHP code and not something else. So we can look into this. But the question is, where in the code do we actually spend the time? Because it's definitely in there. And that brings us to the last pillar that's profiling. And profiling shows you the world from the engine of the PHP, shows you its point of view from the PHP engine, what's going on. And this is interesting because it does not show you what you wanted your code to do, but it shows you what your code actually did, or what the engine actually did to execute your code, which could be something different. There are a lot of, let's say, different questions you can answer with profiling, and those different questions need different profile types. So if you are interested in where did we burn CPU cycles, you're going to have a CPU profile. Where did we spend a lot of? Where did we allocate a lot of memory because we run out of memory in spikes? You're going to see it. You're going to need an allocation profiler to show you what this is. If you want to know where you are transferring a lot of bytes to on a socket, you need I/O profiling. And if you have long-running processes and Kubernetes is out of memory killing your pods every now and then, you need a heap life profiler to find out where your memory is actually leaking over time. And profilers also show you something additional, something that you don't actually write in your code, but they show you runtime events. Like every now and then, the PHP engine will just do a garbage collection cycle for you, or it will compile files, or it will restart the op cache if you have not configured it correctly. These are things that you don't really see in your code. You don't write that, but it just happens because the engine has to do it. And all of these things take time. There are two types of profilers out there. There are instrumentation and sampling profilers. An instrumentation profiler is extremely important and super helpful if you are able to reproduce the problem or the bug or the performance system that you had on your production locally. The problem with instrumentation profilers is that they have a super high overhead because they instrument just every single function entry and exit and collect every information about that. That makes it high overhead, but the upside of that is that you see just everything that is happening. You get a 100% accurate call graph for what's going on in your system. The thing is, you do not want this in your production environment, but if you still want profiling in your production environment, there are sampling profilers out there that'll actually just collect samples every now and then using statistics upscale those numbers so that after a certain amount of time, you get to see the real picture of what's going on with low overhead. So back to our CSV mystery, I checked the profiler, what we were seeing in the profiler, because now we also know where to look actually, and we saw this thing. And this is the exception profiler in PHP. So this was seeing 495,000 exceptions in those 14.2 seconds that we spent in the span. And that is a lot. It also means that PHP is pretty fast because we can throw 500,000 exceptions in not a lot of time. Broken down, that's 35,000 exceptions per second. The interesting thing is the logs showed success, and also the tracer did not collect any exceptions to those things. So where do these 500,000 exceptions come from? The culprit, just going down in the flame graph is super deep. It's 85 frames deep, so it's not on the screen complete. But if going down to the end, we see this function here. This is the comparator library from the PHP unit ecosystem. And it has a signature of this. So it's basically, it's an assert equal function that will return void if the assertion is correct. But if the assertion fails, it will throw an exception. And these were the exceptions that we saw. And that makes perfect sense in an environment like PHP unit, where if the assertion fails, you want the test to stop. Because then the exceptions just bubbles up to the PHP unit framework back again. It can catch it and it can show you that the test failed. In this case, it makes no sense to have this kind of signature or using this library at all. But why are exceptions expensive? Well, every time you throw an exception, or technically speaking, every time you create an exception object, there is no way around for you that PHP captures the full stack trace. In this case, it was 85 frames deep. And for every single frame, PHP has to capture the file name, the line number, the class and method names. And it has to do so every single time for every one of these frames, for every one of these nearly 500,000 exceptions. And if you run this locally, if you just create a small PHP file with 85 frames deep and start throwing exceptions and catching them, you will see that you can spend 3.3 seconds just throwing these exceptions, not doing any valuable thing. And in those 14.2 seconds that we have, this is 23% of all our runtime that we just spend in throwing exceptions. But the question is, this was not there before. It worked once it was deployed, like, I don't know, half a year before, it just worked and we didn't see this kind of thing. So what happened? Well, the code did not change. There were no deployments on that part of the code, but what changed is the data changed. The data that customers were uploading to the API. So over months, more and more of the products that the merchants were uploading diverged from the data that the customer had in their database. So that means more and more of those comparisons started failing, and that means that more and more exceptions got thrown, and over time, this got just slowly. So the bug was not the code. It did exactly what we told it to do. The uncomfortable part is in this case that nothing is broken. There were no alerts, no errors, no deployments, no one changed anything. But the system was completely healthy, it was just slowly getting worse. And observability is not always about catching the big explosions, because if use 1 goes down again, you'll probably notice before you get paged, if you get paged. But it's about noticing rot, these kind of things. Because data changes and workloads might drift. And the one thing that was the edge case in the beginning, where you thought like, well, let's just throw an exception because we don't care and this should never happen at all. This might become your common case in your code just by someone else uploading data that you have not anticipated they would do. And this is why these kind of bugs are expensive, until someone says this used to be faster and you start to investigate what's going on. So observability is not just a dashboard. I want to say that there is this saying that doing something bad is better than not doing it at all. And I would say this also applies to observability, because if you don't see anything, then just having a few metrics is better than not seeing anything at all. Just having some log messages or some traces, or maybe just have one service profiled, will actually give you a flashlight into your production environment, so you'll see what's actually going on there. And the real power from all of these 4 pillars comes that you're able to see a lot of stuff with each one of them, but you're also able to connect all of the dots together. So basically saying that you have in the tracer, you have your span IDs, and you can add this span ID to the context of your log messages, which means that just going to the tracer, you see a trace span, and you can say, show me all the log messages that have been written down while this span was active. And you can also do the same with profiling. You can just say, I see this span, and from here I want to see the profiles. Show me all the samples that have been collected during that thing. So with that being said, measure first, argue later. And that's all. Thank you very much.